pyramids. Which means this. For example, if, and they probably have one in here. Let's say you've got a spinner that's split into A, B, and C. And you have, gosh, I don't know. Let's say you just have, you're flipping a coin as well. You've got this coin. Oh, that has whatever on it. And you want to know the probability of spinning an A and getting a head on the coin. How often will it happen that when you spin that spinner and flip the coin, you're going to get an A and a head? Well, one way to figure that out is you could write down all the possible combinations of doing those things. And a way to do that is to do what the book says, to draw a tree diagram. And they call it tree diagram because it looks a lot like a tree. And you've got your different things. So you've got your spinner first. What are your different possibilities when you spin this thing? You can either spin an A, a B, or a C. And then off of that, you can show the possibilities of things that you could do after that. If you spun an A and then flipped the coin, you could get a head or a tail. If you spun a B, you could also get a head or a tail. If you did a C, you could also get a head or a tail. And then you can see, put those together, and that gets you your sample space or all your different combinations. You could get a A and a head. You get an A and a tail. Get a B and a head. Get a B and a tail. You get a C and a head, and you could get a C and a tail. And you know if you have all those different combinations, how many total combinations? 1, 2, 3, 4, 5, 6. How many of those 6 are the one you want, the A and the H? Just one. So your probability of spinning the spinner on A and flipping the coin and getting a head is 1 in 6. Now, with that being said, you probably don't always want to have to draw tree diagrams for things because it could get complicated. What if I said, okay, what's the probability of, you've got a dice, what's the probability of rolling a 3, and then let's do the coin again just because. Here's my coin and getting a head. Well, let's do tail this time. You don't really want to always have to do the tree diagram because they get to be a bit long. Because what's all my probabilities? If I'm doing my tree diagram, I do my tree diagram. For my dice, how many possibilities do I have for dice? You can roll a 1, a 2, a 3, a 4, a 5, 6, and then off of each one of those you can flip and get a head, tail, head, tail, head, tail, head, tail, head, tail, head, tail, which means you could get a 1 and a head, a 1 and a tail, a 2 and a head, a 2 and a tail, a 3 and a head, a 3 and a tail, a 4 and a head, a 4 and a tail, 5 head, 5 tail, 6 head, 6 tail. How many combinations are there? 12. How many of those combinations are a 3 and a tail? Just one, so it would be 1/12. Because then you don't want to do that, because what happens if it was a deck of cards? You know, what if I asked you what's the probability of drawing, you know, the king of clubs and then the queen of clubs from a deck of cards? You're going to do 52 and write down all possible combinations? No, certainly not. You're going to write this down. To find compound probabilities, to find compound probabilities, comma, you multiply, that's the key right here, multiply their probabilities together, their individual probabilities together. That is kind of our key phrase here, that page. And you'll see this is much easier than we made it, doing what we did there. That means this, with what we just did here. To find my probability of rolling a 3 and then flipping to get a tail, I would take the individual thing, which would be the probability of getting a 3, and multiply it by the probability of getting a tail. What is my probability when I roll a dice of getting a 3? Yeah, there's 6 sides to a dice, only one of them is a 3. What's my probability of flipping a coin and getting a tail? 1/2. The probability of both of those happening is those two probabilities multiplied together, or 1/12, which is what we figured out there. So going back to my card thing for Wade, because he was very excited about that. Let's say you're drawing randomly out of a deck of cards. What's your probability of drawing the Jack of Hearts and then drawing the Queen of Spades? Let's do the Queen of Diamonds because I can draw a diamond easier than that. Well, that probability is the same as the probability of drawing the Jack of Hearts multiplied by the probability of the Queen of Diamonds. What is my probability of drawing the Jack of Hearts? How many Jacks are there in the Jack of Hearts are there in the card? 1 out of 52 total cards. Now, we have to assume that I'm going to put the Jack of Hearts back in before I draw the Queen of Diamonds, because that would change some stuff. What's the probability of getting the Queen of Diamonds? 1 in 52. The probability of you doing those both back to back would be those probabilities multiplied together 1 times, I don't know what 52 times 52 is, but it's pretty big. 104, 0, 10, 25, 26. 1 in 2,704 times. It's not going to happen very often. I mean, it's only going to happen once in a great while that you actually pull the Jack of Clubs. But to do the Jack of Clubs, then guess that there's, and that's a lot like winning the lottery. Why you should never play the lottery? Because you can figure that out kind of now, a little bit, anyways. How many numbers? Anybody? I don't play it, so I have no idea. But I think you get. I think it's like 6 numbers. Do you have to pick 6 in a row, or pick 5? Pick 6.
Wait, that's the fireball one.
Well, I don't know. Give me one of them.
There's Illinois lottery.
What's the Illinois lottery, partner? How many numbers do you have to pick? You don't know.
Oh, 12.
Pick 12. Anyways, I think they go up to like 60. Numbers go on through 60. Even if you had to just draw 5, well, your probability of getting the first one right, let's say you say, okay, I'm going to get 29, it's 1 in 60. Your probability of then getting the next one right, well, we could just do 1 in 60 again. That's of getting 2 right, of getting 3 right, of getting 4 right, of getting 5 right. Right away you can see 60 times 60 is 3,600. 3,600 times that is about 19,000. 19,000 times 60 is what? Almost 120,000 or whatever it is. And 120,000 times 60 is in the 7 million range or whatever it is. So the probability of you doing that is incredibly small if you actually really do that. But their motto is somebody's going to win, it might as well be you. Well, yeah, just that doesn't change the fact that you won't win. Somebody will win. Take a look in your books, please, on page 526 and 527. Actually, just look at page 527. It says there, for problems 10 through 14, consider a compound experiment in which a nickel is flipped and then a quarter is flipped. Create a tree diagram that shows all of the possible outcomes for the compound experiment. So what would that look like? Well, you're flipping a nickel and you're flipping a quarter. The tree diagram would look like this. When you flip a nickel, you can either get a head or a tail or a head. And then after that, when you flip the quarter, you could also either get the tail, head, or the tail and the head, or a flip-flop. Do they label those by chance? So then when you're listing all of your outcomes, you just follow the little tree around. This would give you 2 tails. This would give you a tail and a head. This would give you 2 heads. And this would give you a head and a tail. There's your tree diagram with your outcomes. The problem 11 says make a table that shows the probability of each possible outcome. Well, that wouldn't be too hard. Here's your table. What's the probability of getting a tail and a tail? 1 and what? Probability is 1/4. What's your probability of getting a tail and a head? 1/4. What's your probability of getting a head and a head? 1/4. Your probability of getting a head and a tail?
1/4. Say 1 million. 7 million.
And then question number 13, what if they ask you this, what's the probability that you get at least 1 head? If you looked at this, what is your probability of getting at least 1 head? Well, there's still 4 things, right? How many of those things have at least 1 head in them?
3.
So your probability is 3/4 of getting at least 1 head. Yeah. We got something there. I think I will just give you a quiz and we will call it as a, I think. See what it is.